Thank you very much for being here to listen to me talk. You may have noticed that I have changed the title of my talk slightly, which is a cautionary tale of don't submit your talk proposal before you actually know what you're going to talk about. I think hopefully the moral of the story will be everything will work out okay anyway, but you'll have to let me know how it goes. My name is Davy Stevenson. I'm a software engineer for Elemental Technologies in Portland, Oregon. I'd take a little aside here to say that I think that RubyConf has been really amazing so far. I think everyone has just been, it's been a friendly group of people. I absolutely am in love with the Ruby Friends thing. I think it's a great way to help break the ice between some programmers who oftentimes are a little bit shy and don't really want to talk to other people. So if anyone wants to be a Ruby friend with me, find me later. So what is this talk all about? So one type of talk that I really enjoy, but I don't see that many talks of this category, is kind of the talks that talk about what companies are actually doing with Ruby, with Rails, what problems are they solving, what are they using this technology for in a really explicit way. And so I'm hoping in this talk to give you guys a little bit of an inside scoop as to how Elemental uses Ruby. I think we use it in a little bit of an interesting, unique way. And I'm doing that by giving you guys a story about a recent problem that we encountered with some of the technology that we were using. A use case that we were using DRb for, as our product grew, it ended up not really fitting our needs anymore. And so we needed to figure out how to solve this problem and what to replace DRb with in that context. So, Elemental Technologies. We're a startup company in Portland, Oregon. We do video transcoding software. And our big claim to fame is that we use NVIDIA GPUs to parallelize the video transcoding process, which allows us to get much faster video transcoding throughput as compared to all of our competitors. And so the speed of our products is vastly superior to all of our competitor products, which has allowed us, even though we're a very small startup, to be very competitive with a lot of the bigger names in the space. So we actually sell server appliances. We sell these appliances to large companies to solve their video transcoding needs. These servers are installed oftentimes in their data centers, and we need to be able to integrate these servers into their workflow environments. So who are some of our customers? HBO uses Elemental servers to transcode all of their content that they have for broadcast delivery, and they transcode that content for online adaptive bitrate consumption to power HBO Go. So HBO has a vast library of broadcast television, and this is great if you're trying to transmit this video to cable subscribers. But in the age of Netflix and Hulu, they needed to be competitive and be able to transmit their video over the internet as well. This is a big problem for companies because the number of different devices that their consumers are going to be using to consume this video is very broad, and the transcoding is needed to create the video specifically for each type of device. So the videos needed to be displayed on an iPhone or an iPad are very different than the video displayed on your computer or your TV hooked up to HBO Go or your Android device. So companies like HBO need lots of servers to handle all this transcoding. We also power Comcast Xfinity application and the ABC News iPad app, among others. So another big win for Elemental was that we helped power the online coverage of the London Olympics in multiple continents and many countries. The BBC used Elemental's gear to live stream 24 channels 24/7 throughout the entire London Olympic Games. So for customers like the BBC, having servers, having these live streams up 24/7 is of the utmost importance. We need to make sure that these servers are stable and able to continue transcoding for weeks or months on end. So you may be asking yourself, this is RubyConf, And all video transcoding, I'm pretty sure you guys aren't doing video transcoding using Ruby. And if you thought that, then yes, you are correct. We don't use Ruby to do any video transcoding. However, Ruby has helped Elemental in a lot of ways to basically grow from a very small startup into a very competitive player in this market. And so how has Ruby helped Elemental? So we use a Rails application running on each server to handle the user interface of these of our servers and handle all the transcoding events. This has allowed us to have a best-in-class user interface that's much more usable and much easier to integrate into these workflow environments as compared to a lot of our competitors. Ruby allows for a lot of fast-paced development. You can get a lot done really quickly with Ruby. This has allowed us to scale very quickly as a startup and to develop our products and add the features that we needed in a very short time frame. And not only that, but I'm really happy that I get to use Ruby on a daily basis in order to solve these really interesting problems. We all love the Ruby language. It's a joy to use, and it helps us attract world-class developers to work on our products. So let's go a little bit deeper into an example server node that we have in our use case. So I already mentioned that we use the Rails to provide a user interface for these servers. Our customers can access this through the HTML interface or use the RESTful API to automate their workflows. We also run a multi-threaded Ruby script as a service daemon on each of our servers. This service daemon is responsible for managing the vast majority of the actual transcoding that happens. In our file-to-file case, it needs to do a lot of load balancing to make sure that it's consuming the maximum number of resources and thus getting the maximum number of throughput for our encoding processes that are running. For our live streaming products, it needs to be able to manage the resources and handle starting and stopping these live streams and making sure that all the information is flowing appropriately throughout the entire system. So let's step back into our story. So in the beginning, we are trying to build a product. And oftentimes, the initial requirements and feature sets are what drive the technology decisions. And this makes sense because none of us have crystal balls. None of us know definitively what the future is going to hold or where our products are going to evolve into. We're not sure what new technology is going to be created in the future that may solve a problem better. We don't know necessarily what our customers' needs are going to be in the future. As we continue developing our products, there are new features, new use cases that we are developing. And oftentimes, it's easy to reuse the technology that we're already using to solve these new, similar problems. Oftentimes, the problems are very similar. Maybe sometimes they aren't quite as a perfect match, but even then, sometimes it's still useful to use the known technology as opposed to spend the time to learn something new. And sometimes, it can be a good business decision to reuse existing technology in a close enough match as opposed to spending the time to explore new options. If you're in a fast-paced startup environment, sometimes getting the product out the door and in your customer's hands is more important than making sure that the technology you're using is a perfect match. So Elemental has been using DRb as a communication method for about 3 years now. DRb is really easy to use, it is fast, and it is reliable. It's a really easy way to allow 2 different Ruby processes to communicate to each other. Here's a quick little code example to show kind of what the power of what DRb can do. So we have this server class, and it exposes 2 methods. You can get data from the server, which returns a simple array, or you can send data to the server, and the server just prints that data out. Now we're going to create a DRb service on a specific URI, and we're going to pass in this instance of this server class that we've created. So now anyone who's connecting to this DRb service has access to those methods in our server class. And to keep this process running, we're going to call DRb thread join so that this service is running if we're going to run it from the command line. So now we can open up IRB, require DRb again, create a new DRb object to connect to that URI from our server. And now we have an object that can communicate directly with that server object. We can call that getData method from a completely different Ruby process and get that array back. And we can send data to that server as well, pass in the string hello, and then over on the service as it's running, it's going to be printing out that in that other process. So you can use DRb to send data and messages. You can use it to request data, which can be very powerful. If you know exactly what data you want, you can ask the service to give you a very specific set of information. You can pass entire Ruby objects back and forth using Marshall, which can be incredibly powerful if both Ruby processes have the same concept of those objects. One thing about DRb is it is a point-to-point communication method. So you have to know exactly who you're talking to. You open up a connection to a direct service, particularly, in order to perform that communication. So how does Elemental use DRb? So looking back to our little state diagram from before, we can see that we use DRb to communicate between our Rails user interface and the Ruby service daemon that's running on all of these servers. So our first product was a file-to-file transcoding server. This would basically transcode files to multiple formats as fast as possible, take up as much GPU resources as possible, get those files transcoded, high frame rate. All of those encoding processes are returning a lot of statistic information back to the service daemon very continuously. And this is information such as the current frames per second that's being encoded and certain quality metrics to describe, is the current encode, is the quality good, or is it, having to reduce the quality in order to, for some other reason of some sort. This is information that we don't necessarily want to store permanently. There's no reason for us to have a historical, we don't need to run statistics on this information later. So we don't really want to store this data in the database. We don't want to waste the cycles to submit that work to the database when we could be using those CPU cycles to transcode files faster. But our customers still want to be able to query that information. If they're seeing some issues with, they want to see what the current frames per second are, they want to see what some of that data is, they still want to be able to query that information. And so we can have the Rails UI ask the daemon, what is the current stats for a particular encode, get that data back, display it in the UI. And that's a really great use of DRb. So our next product was our live streaming server, which is, this is a kind of a different use case. They're getting live data in, and we have to transcode it in real time to multiple output formats and keep that running as long as possible. So in this use case, now the UI needs to actually send some commands to the service daemon. We need to be able to tell it when exactly to start the event, maybe to switch inputs if one of the inputs goes down. Maybe our output CDN is down, maybe Akamai is down, but some of the other CDNs are up. So we want to tell it to stop encoding certain outputs, but keep other outputs up. Now we need a way to communicate from the Rails UI to the daemon send commands. And DRb is a pretty good fit for this use case. You may say there's other ways to send commands, and that may be right, but in this case, using DRb for this met our needs very well. There was no need to try anything else. So as our customers had more and more need for transcoding, they needed more and more servers. And they wanted a central way to communicate with all of these servers and manage these servers, to manage failover of the servers in case components die. Because a lot of these people, they are running encodes for months on end. And we all know that server components die. That happens. We have to plan for that. So we have now a management node. It's not doing any transcoding itself. It's just managing the state of all these other servers. It's also running a Ruby service script. Instead of managing the live encodes, it's managing these other servers. And so in order to do that, that service needs to be able to communicate to the services on all the live streaming nodes. So we can use DRb for that too. This use case was a little bit different though, especially as the needs of our customers changed over time. We need to make sure that those live nodes are up no matter what. It doesn't matter if other components are failing. If the external database server goes down, we don't care. We still want our live streams to go out, and so we may need to make sure that our service daemons are still running on all those nodes. However, there's still data that's being produced that we need to make sure is going to be eventually persisted to the database so that the customer can tell if something went wrong during this sort of downtime. You know, things like, did one of the CDNs go down and did an alert pop up? Did issues happen with the transcoding where certain outputs were failing for certain parts of time? They want to know that information. So now we have the use case where DRb is not only just sending messages, but it has to be ensuring the receipt of that message, ensuring that the database is getting that information. And that's not something that DRb really is suited for. So now we came to our problem. We have our technology that we're using, DRb for communication, and it's not fitting our needs anymore. We have things that we need to solve that DRb can't provide for us. So if you find yourself in this sort of situation, what are you going to do? The first important part is to, of course, define the exact problem that you have. So I outlined the 3 use cases that we have for DRb. 2 of those use cases are still fine. DRb still fits our needs in those use cases. We need to define the problem as the exact portion of the code that is actually not fitting our needs anymore. And then we also have to think about what our customer needs are. What do they actually want out of our product? What is most important to them? And that's going to help determine our decision-making process for what our solution is going to be. And most importantly, before embarking on a project like this, is to define what you mean by success beforehand. That's a good way for you to be able to then meet your goal later. And so in this case, for success, we want to be replacing that inter-daemon communication with something that's much more reliable and robust, can manage saving messages even when other components are not available to receive those messages, and be able to store those messages, and we can be guaranteed that data is not going to be lost. For us, speed isn't a primary concern. For our users, what they really care about is the reliability, stability, and the resiliency of our servers. As far as the Ruby layer goes, if it's working, that's great. What they really care about is those encoding processes continuing to run all the time. And so also when you're embarking on a project like this, it's very useful to limit the scope of the project. Replace one single component at a time. Again, the inter-daemon communication layer is what we're going to focus on here. Replacing a single component helps make sure that you're not trying to do too much too fast. And then once you've replaced one portion, you can work on incremental development. Maybe then you can find other areas where using a new technology is going to be better than the existing technology, and move on from that. So why would we start looking into a message queue? And it became really obvious to me that a message queue is the right solution for this problem, because I noticed that I was beginning to reinvent the wheel. I was starting to develop what was kind of a pseudo message queue around and in the middle of our DRb code. Except my message queue code is, of course, not going to be nearly as stable and robust as the many, many different message queue options that are available to use. The other great thing about using a message queue is it's decoupling the producers from the consumers. In this sort of case where we have these multiple live encoding servers and one management server, the live encoding servers don't actually care who receives the messages that they're sending out. They don't need to know who the consumer, the management node, is. And so DRb, with its point-to-point communication, adds this limitation to the producer. The producer has to know exactly who it's communicating to. And a message queue also helps reduce the responsibility of the various components. Our service daemon was responsible for a lot of things. And if it's responsible for a lot of things, then that means that failures in one area are going to trickle down and cause impact that's unintended consequences in other areas of our code. We want to make sure that other areas in the service daemon aren't going to mean that we're losing data in the messaging section. So we decided to use RabbitMQ as our message broker system. It's an asynchronous message broker. It uses AMQP as its messaging protocol. However, it can also use a lot of different other message protocols, which was very attractive to us. So if we do determine that AMQP is not the right fit for us in the future, we would be able to swap that out. Another great benefit of RabbitMQ is it has high availability clustering available. So as we move towards wanting to ensure the availability of all of our messages, we can use the multiple servers themselves to enable high availability clustering. So quick overview of AMQP, the Advanced Message Queue Protocol. This is simply a protocol used to receive, route, queue, and deliver messages. Again, there's other protocols available that do very similar things. The one good thing about AMQP is that there is a lot of implementations in multiple other languages, which for us was a really good benefit because we do have major components written in other languages. Our main encoding processes are run in C++. So being able to easily be able to use AMQP in our other areas is going to be a great strength for us as well. So in order to use AMQP with Ruby, you use the Ruby AMQP gem. This uses EventMachine, coming back to my original talk, so I wasn't completely out of the woods there. So you use the AMQP gem to communicate with the RabbitMQ broker that's running on your server. And so here's a quick example. So you require AMQP, and it requires EventMachine to be running. And so we call EventMachine run and run everything inside that loop. We create a connection to the AMQP, the RabbitMQ broker, and create a channel that we're going to communicate on. We're going to specify the queue that we want our messages to go to, and then RabbitMQ it's an exchange system, so you actually publish to exchanges, not to the queue specifically. This is actually kind of interesting because it means that you can define different message routing protocols as necessary. You could have multiple different queues, and the exchange could fan out the message to multiple queues or do other advanced routing. This is just a really simple example where the exchange is just tying directly to this one queue. Now we're going to use EventMachine to add a periodic timer. Every 5 seconds, it's going to publish the current time to the exchange. And then we are going to subscribe to that queue. And whenever we receive something, we're going to print out to the screen. So if you run this, you get a little script, and every 5 seconds, it'll be printing out the time. So now we've defined the scope of our solution. So here's our main issues that we want to make sure that RabbitMQ is solving for us. We want to make sure that RabbitMQ is going to add reliability to our system. RabbitMQ provides this concept of durable queues. These are queues where if the message goes in the queue, you're not going to ever lose that message. It will handle persisting that message to the disk and making sure that that message is never lost, even if the RabbitMQ broker goes down. RabbitMQ also ensures the order of the messages it receives, which is really good for us to make sure that we're getting a correct state change messaging system from what's happening on our live events. We're knowing that the order that the management node is receiving the messages is the correct order of the events that happen on those live nodes. So stability, we want to make sure things are more stable. And this is really accomplished by the decoupling of the messaging from the service daemon into a different component. RabbitMQ is going to handle all of that messaging, decoupling that possible failure case from the service daemon itself. By making sure each of these two different components is focusing on the things that are important to it, it means that the failure in one component is not going to cause unintended consequences and trickle and affect other areas of our system. And resiliency. We want to make sure our entire cluster is very resilient to errors. And that is going to be accomplished by enabling the high availability of the RabbitMQ brokers so that the messages are shared amongst all the different servers. And so that way, if one particular server has some sort of issue and crashes, we're not going to be losing that data. And we're still going to be using DRb. In some of our use cases, DRb is still the right tool for the job. It is very simple, which I really like. It's very easy to use. The syntax is very Ruby-esque. And not only that, but we still have that use case where we need to request specific data from our service daemon. And in that, DRb is still the real solution for that task. So a little bit about our final implementation. So we have these multiple producers, which are the live streaming nodes, and the single consumer, which is the management node. And even when we expand out to have redundant management nodes, there's still always going to be one consumer. And that also means the producers don't actually have to worry about who their single consumer are. The management nodes themselves are going to manage making sure that there is always someone there to consume those messages. It's not something that the live encodes have to worry about. And we do have our two main different classes of data. We have the state change information that we need to be durable. That's those sort of things like if an alert happened on one of those nodes, change input happened, encoding failed for some reason, all these sorts of things we need to make sure are stored and always persisted to the database. Those can go along durable queues. And then we have the more transient status information, that information I was telling you about earlier where, so what's the current frames per second, what's the current quality metrics, the sort of information where we want the real-time information, but we don't necessarily need to store the historical information from that. Those can be stored in a different way in RabbitMQ, in a way that's not going to tax the system. So here's kind of an overview of what our final implementation is going to look like. We have our main management node, and again, this is kind of simplistic. Eventually, we're going to have some redundant management nodes, but that's, the management nodes will deal with that sort of thing. And then the multiple worker nodes. And then we have the clustered message brokers on all of those servers. And RabbitMQ will handle the high availability clustering of the brokers between all these different servers. We still will have a DRb connection between the UI and the Ruby service on each of those nodes individually. But each of the different components can send messages to the message broker as necessary. So that allows us to do incremental development. If we determine that sending messages from the Rails UI is going to be a better solution for some of our use cases, we can do that. And another great benefit is in the future we're hoping to have our communication from the encoder processes themselves also use AMQP and be able to send the messages into the message broker from those processes as well, which again are C++ applications. So what are some of the results we've seen after doing some of this refactoring? The performance of RabbitMQ has been really, really impressive to us. The speed and throughput that RabbitMQ provides is more than sufficient for anything that Elemental will need it for in the near future. The broker can handle millions and millions of messages, and we're not sending anywhere near that amount of information. So for us, the performance has been great. The decoupling of the communication was something even more satisfying than I had originally intended. We all know that we have code that we want to refactor, and we have an idea of how we're going to refactor that code. And then once you actually take that refactoring takes place and you see the new structure, sometimes you're like, man, that was satisfying. This is just a beautiful implementation. The way that this information is now structured very cleanly and separated, it really helped drive home to us that the message queue was the right solution for this problem for us. We haven't actually released this code yet. It's slated for our next major release, which is going to happen by the end of the next year, or end of this year, sorry. But I'm looking forward to that because I think it's going to be positioning our products for a lot of growth. Our customers are asking for a lot more interesting reliability and resiliency in our clustered systems. And I think RabbitMQ is going to be able to provide a lot of these features for us as we grow. And I'd like to give a quick shout out to my coworker Matt, who did a lot of the implementation details and also made those great diagrams for me. Thanks, Matt. And I wanted to know if anyone had any questions for me.
Hi. Two questions. First, I'm with Seki-san, who actually made a DRb, and he wants to be friends with you.
I would love to be friends with you.
The second question is, like, you mentioned that, like, so David to David, DRb was not a good fit. What was this? Is it just reliability? It wasn't reliable or something?
Well, part of the daemon-to-daemon thing was that, so he was asking why exactly was DRb not a good fit for the daemon-to-daemon case? Was it the reliability? And it was kind of a little bit of the reliability, but one of the main things was actually the point-to-point communication, in that in order to use DRb, you actually have to know who you're actually talking to. You have to know, the two servers have to know exactly who each other are. And in some of the cases where the live node is sending its information back to the master, like for example, if we have one master node in the backup master, if the master node goes down, then all the live encodes need to know that now they need to be sending all their messages not to the master node, but to the backup master. That's information that those servers don't need to know about. They don't need to know who they're sending their information to. They just need to know that the master is going to be getting that information. So that's one reason why DRb wasn't really a good fit for that use case. And then additionally, so DRb, when we found we were using it to send the messages to the master, if the master wasn't up for some reason, then the live node would have to be storing that information locally in memory. Because DRb is part of that Ruby process itself. And so, but there you get into a challenging situation where if the master is down for some reason, let's say we're upgrading the software on those master nodes, and now all these live nodes are kind of queuing up all this information that they need to send to the master node once it's coming back up. What if the service daemon crashes at that point? Because all that data is in memory, we're going to be losing all that information. And so in order to avoid that problem, then we're going to have to be implementing the methodology to somehow persist that data to state so that DRb can then re-access it. And that's kind of where you're getting to the point, well, where the message queue has already implemented that. The message queue handles that case for us. So we don't necessarily want to be coding that up for ourselves so we can use DRb. Anything else? What volume of messages are we seeing? So for each of our encoding processes usually sends 1 message a second approximately. And our main live servers can run about 6 to 10 live events concurrently. And then our current largest cluster is about 20 nodes. So, so that's kind of what we're seeing for our current live encoding servers. However, we have a new product that we're releasing, which is just a packager. And so that's not actually doing any transcoding. It's just repackaging for a different delivery mechanism. And that server can run many, many more concurrent live package events at once. That's something, we're seeing something along the lines of it can run 60 to 100, maybe 120. And so then you're getting to the case where each node is running 120 messages a second, plus you're clustering them all together. So that's kind of the scale that we're seeing. So it's not really that much, not really that many messages. You can talk to lots of other companies who are dealing with high volume messaging that blows us out of the water.
Just to respond, I have used RabbitMQ production, and we did a couple hundred megabytes per second through it, and it didn't fall over yet.
Anything else? So did it increase the complexity of our platform? And I think what you're saying is, well, so because DRb is included within Ruby, and so we kind of get that for free. Now, with using RabbitMQ, there's a whole bunch of other things that we need to package up and distribute on our servers. Is that kind of the question you're asking? And yeah, that definitely complicates our packaging. We're going to have to now package up not only RabbitMQ itself, but all the new GEMS EventMachine and AMQP in order to handle this. So there's definitely overhead that we had to deal with there to handle making that switch. Well, thank you, everyone. I'm really glad that you guys came, and hopefully you learned something, or at least discovered something new that you can do with Ruby. So thanks again.